A look at the concept of flowcharts. All right, so in part one of this theory unit, we talked about problem solving in general, and I broke it down into 5 steps. In part 2, I introduced a model, which usually fits into step 2, 3 of problem solving, that is very general for problem solving, the idea of the top-down design. And that particular model is used in the field of computer science. It's not just used in the field, but it's this general idea of solving a problem by breaking it into smaller chunks. This is also a model. Flowcharting is also a model, but it's a more specific model. It's a little more complicated than the top-down chart. Now, but that being said, I'm sure most of you have seen a flowchart before, so it's not going to be revolutionary to you. So what we're talking about here is logic. And logic is the way we figure stuff out. Logic is a method of solving problems. In some sense, math is a model for solving problems involving numbers. It's the model we use for that, okay? In other senses, other models are used, like top-down charts, for example. We've already used the top-down chart, and there are other models that you can employ, and today we're going to focus on a different model known as the flowchart. A flowchart is an option model for solving problems. Now, before we go any further, let me ease your minds. For the course overall, you are not going to need to do flowcharts. This is the one time this year that you're going to be making flowcharts as an exercise, but I'm not going to require flowcharts or top-down charts for any programs you write. Once we get into our next unit, it's pure coding from that point forward in the course. Okay, so this is the theory unit where we look at this. That's not to say that these aren't useful tools. And they are used in the real world in programming environments. But you guys in this classroom are not going to need to do them. Okay, so this word, algorithm, is a word to represent essentially how you solve a problem in a step-by-step way. It's not exclusive to the realm of computer science. Flowcharts is essentially a visual representation of that. Now, other ways you can do step-by-steps include how-to instructions, right? When you get like, you buy something at IKEA and how to set it up, like a coffee table. You get how-to instructions that shows you step-by-step how to set it up. Recipes are how-to instructions, how to bake a cake. It shows you step-by-step how to do that, okay? So that's what an algorithm is. Recipes and instruction manuals are algorithms, okay? They're algorithms to show you step-by-step how to do something. The flowchart is an algorithm. It's just an algorithm done in a visual way, okay? It's a way that you can see the sort of solution in front of you. For some of us, it helps because we're visual people and we like to see things in a more visual way. But for others, it's kind of a time waster. Okay? But the way a flowchart should work is you should look like a roadmap that'll get you through from the start to the end of solving the problem. Okay, which, by the way, is exactly what a computer program is. Excuse me. A computer program is also a step-by-step set of instructions, and you write the code using an algorithm. Okay, so they mesh, they come together in this way. Okay. So the flowchart is this visual. Let's get started with it, okay? If we fit this into the 5 problem-solving steps that we've been looking at before, okay, here's how it would fit. Step 1, what is the problem? This is just general. In computer science, that's the same. You still have to define the problem. Step 2, make a model. Well, that could be where you develop your algorithm and use a flowchart or a top-down chart or neither as you start to develop your algorithm and then move to step 4 where now you're actually going to write the computer program, which, by the way, is exactly what we just did in our little Pong example. We actually wrote the computer program. We used the Scratch environment, which was drag and drop, and then we did step 5. We ran it. And if it didn't work, then we would have had to go back and start over again. So with doing flowcharts, there are some symbols you need to know. Let's go over them. The common symbols are 1, this one, you're going to only have 2 of them in a flowchart. They represent the beginning and the end of the flowchart, or the start, stop, or the begin, like I said, whatever you want to call them. It's not drawn really well up here on the projector, but that's a rounded rectangle. That's what that usually is. An actual rectangle is the most common symbol you're going to find in flowcharts. It just represents you doing an action. So something is happening on that step, okay? It's called a flowchart because it has a direction to it. So unlike the top-down chart where you use lines, flowcharts need arrows because it indicates a direction that you're going, okay? This symbol we'll get to a little bit more in a minute. The diamond shape is used to make decisions. It's essentially a fork in the road where you can go one way or another, and we'll see that in a minute. This one you don't see in all flowcharts. This one is more specific to like computer programming. It represents when there's input or output happening. So this is where you kind of are involving the user. So you're getting information from the user or you're showing information to the user. So in general problem solving, you don't need that one. But in computer science, maybe you might need that one. Okay? Circles are optional shapes that are usually used to just sort of clean up the flowchart. They're nothing you need to generally worry about. Okay, so let's do the world's simplest flowchart. Okay, just basically step by step. So here's the problem. How do I get in a locked room? Okay, first thing I would do is basically think about all the steps necessary for doing this. But let's skip right ahead. Let's put it into a flowchart. So those are the steps. Let's put it into a flowchart. Okay, so I start. I walk to the room, stop at the door, take out the keys, choose a key, put it in the lock, turn the key, open the door, take the key out, walk in, and I'm done. This is like a board at a game, like a board game, right? You just go from like a Monopoly. You're just moving step to step to step, okay? The simplest flowchart possible. It's all just steps. It's all just actions, moving from one action to another. But I kind of took some liberties here. Like, for example, when I said choose a key, that may be more of a decision happening there. So in the next one, I'm going to make it a little more difficult. Let's try this next one. Okay. You're in a house. You have a telephone, a doorbell, and an alarm clock. And they all have the same sound. You hear ringing. Which one is it? Okay, well, let's try and solve this. I start. I hear the bell. I make my first decision. Is it the telephone? If the answer is yes, I answer the phone, and I'm done. If the answer is no, I have to make another decision. Is it the doorbell? If the answer is yes, I see who's at the door, and I'm done. I don't have to make a third decision. If it's not the telephone, and it's not the doorbell, it's the alarm clock. So I turn off the alarm, and I'm done. Here in this flowchart, you see the use of the decision symbol. What this creates is that fork in the road. So to get from the start to the end, I have a few different paths I can take, right? It's like driving from here to MTS Center. There's a few different paths you could take. Some of them, depending on the way you go, will make different results, right? So it's the same idea here that we are taking a path through the flowchart to get from one place to the other. In the previous flowchart back here, there was only one path. You just kept following along. But in this one, again, now you see the importance of the arrows because it really leads you along. Let's try another one. Before we do, let's talk about the decision symbol. This symbol is designed to be always drawn this way. One arrow in, two arrows out. Okay? You might be tempted to draw sometimes this symbol, like say you had a flowchart that said, pick your favorite color, and it went down to a decision symbol. You could have like 20 arrows coming out saying red, blue, green, aqua, I don't know my colors, whatever. But I would recommend that, and in general problem solving, that's okay. But in the realm of computer science, you want to kind of actually just have it one arrow in, two arrows out. Which is why, if I go back a little bit, in this one, I used two decisions, right? I should have just basically asked the question, which one is it? And I could have narrowed going phone, alarm clock, doorbell, right? But I want you to try to do it with just one arrow in, two arrow out. And the reason is, that's the way it's going to translate into coding a lot better if you do it that way. Okay, let's try another one. Make Walk's peanut butter sandwich. All right? There's some steps for this. Let's put them down. Let's move ahead to the actual flowchart. Okay. Now in this one I use the input-output symbol for fun because I like to eat sandwiches. So, you know, I like input, and I'm not going to talk about output because that's gross. So I get my stuff, peanut butter sandwich stuff, put the two slices on the plate, spread peanut butter on one of the slices. Ooh, do I want jelly? The answer is yes. I spread jelly on the other slice. and then I come down here. If the answer is no, I just come right down here. Slap the two pieces together, sticky side in, of course. And then I ask this question, do I want another sandwich? If the answer is no, I eat the sandwiches and I'm done. If the answer is yes, notice I go back to here. Okay? What do you notice about going back to here and then starting the process over again? And if I want another one, I go back and do it again. How would you describe what I'm doing right now? A loop, yes, or a cycle, which is one of those core components we talked about again. So here you can see flowcharts does connect to what we're studying in a lot of ways. Okay, let's try another one with the ATM machine. So this would be kind of coding it out in an ATM machine like we did earlier. All right. Now with this one, the input-output does make a little more sense. Because at an ATM machine, you enter a password, a PIN number. If you get it wrong, it will show the user an error message, and you're done. If I get it right, I enter whether I'm doing a deposit or withdrawal, and how much. If it's a deposit, I go one way. If it's a withdrawal, I go the other. If it's a deposit, I just add it to the balance. If it's a withdrawal, I have to check, do I have that much money to take out? If the answer is yes, then I can take it away from my balance. If the answer is no, error message. If the answer is yes, I'm kind of using this generally to just say, okay, here's your money, and we're done. In this example, you can see how it starts to get a little more complicated, but it gives you a visual of what's going on. In this one, I used the circle. It was optional. I didn't have to use the circle there. I could have just pointed these all down to here. Sometimes it gets a little cramped, so you just throw a circle in there just to clean it up a little bit. Not at all necessary. All right, final one. This one is a famous computer science problem, so I'm going to share it with you. In 1202, Leonardo Fibonacci of Pisa, Pisa's in Italy, wrote about the number of rabbits that he would have at the end of 1 year if he started with 2 rabbits. Okay? Now, I don't know how much biology you kids have studied, but if you know anything about rabbits, they breed a lot, and they breed fast, okay? And they breed quickly. So the way he found is there was a pattern here. The pair would produce a pair of offspring after the second month, and then they would stop breeding. And each new pair of rabbits would produce rabbits after the second month, and then stop breeding. So what he did is he tracked this sort of rabbit stuff, and here's what he saw. Here's the months going up in the 12 months, right? So after the first month, he only had one pair of rabbits. Second month, he still had one pair of rabbits. But by the third month, he had 2 pairs of rabbits, right? And then in the 4th month and the 5th month and stuff like that. And what he noticed was this was a pattern, okay? And so he was a mathematician, so he didn't have computers. He solved it using math, okay? Now, let me show you how the math would work if we did it with math. If I did it with math, I would kind of, and I'm not your math teacher, but I would sort of say, okay, well, let's use some variables. F1 is the first month, F2 is the second month, F3 equals F2 plus F1. That was the pattern, he realized. That basically the pattern is, it's always the sum of the 2 months in front of it. Notice how that works. Month 3 is the sum of month 2 and 1. 1 plus 1 is 2. Month 4 is the sum of the 2 in front of it. 2 plus 1 is 3. I'll move up here to month 7. 13 is 8 plus 5. Over here, 89 is 55 plus 34. It was always the sum of the 2 months in front of it. He figured out the pattern. The pattern is known famously as the Fibonacci sequence. Okay? So that's how he figured it out. If I wanted to write a computer program that said, what are the first 100 Fibonacci numbers? I could do that. And actually, I have my grade 11s often have that as a problem to solve. And I say, what's the first 1,000 Fibonacci numbers? You don't want to do that by hand. You want to use a computer or an algorithm. Here's that algorithm in a flowchart. To get the first 100 Fibonacci numbers, let the old term equal 0, let the new term equal 1, find the sum of old and new. Is the sum greater than 100? No. Let the old term equal the new, let the new term equal the sum, output the sum, go back and do it again. When the sum is finally not greater than 100, or pardon me, when it is greater than 100, stop. Okay? This is a more technical example. This is not one that's sort of fun, but it shows you how the flowchart is a visual representation of solving the problem. Now, Fibonacci, Leonardo could have done this. He didn't have the computer software to work with, but he had flowchart as a tool. Okay? And we are done. Now, let me show you what the assignment looks like. I bet you can